Welcome back to CS103 Machines, Languages and Computation. In this second lecture, we're going to consider the question, what is computation? We're going to have a look at some computational devices, and we're going to find a rather surprising fact about them, which is going to lead us into the rest of the class. So what is this thing called computation? We could say computation is what computers do. Well, that's a rather silly thing to say in some ways. And in fact, we'll consider what in fact a computer is and what it is when they're doing computation. But to give the game away, a computer is a device which can follow an algorithm, and computation is what happens when a computer follows an algorithm and computes a result for us. We'll see more about that in the article and the tutorial exercise. What we can think of a computer as, though, is it's a machine. You give it some input data and then it manipulates that input data according to a list of instructions, and those instructions are known as a program. If we can change that program by using, for example, a text editor, then we have a programmable computer, one whose behavior we can change by changing the program. And a program states exactly the sequence of operations to be performed on the input data to form the output data. If you've ever written a program, you'll know exactly what I'm talking about here. It's a precise sequence of operations. And we have to write programs in what's called a formal language. A formal language is one where each word of the language has a very, very precise meaning, unlike English. So in English, I might say someone is tall. Well, that's fairly imprecise. That wouldn't work in a computer language. We have to be exact. So here is an exact program. This one's written in a very simple programming language. It's called Marie. What does it do? Well, it says we load up A into the place called the accumulator. We add B to it, and then we store it in the location called C, and then we halt. So already we're seeing that it's a sequence of instructions. Down below there you see A, B and C. That's the data segment here. A has the decimal value 2, B has the decimal value 2, and C has the decimal value 0. So have a short think and see what you think will happen as a result of this program running. So the answer is A will get loaded up into the accumulator, that's the value 2. 2 will get added to it, so the accumulator now has 4 in it, and then 4, the decimal value 4, will get stored in location C. So at the end of the program, the result is that we've added 2 plus 2, made 4, and we've stored it in C. We could do that perhaps rather more simply by simply drawing it like this as a function box. A function box takes some inputs, here A and B, calculates the value C by adding A and B together, and then outputs the value C. So when we're thinking about a problem, this might be an easier way to think about it. Programs are functions that turn input data into output data. So there's three important bits. What's the input to this box? What's the clever stuff that it does in the middle to do the calculations? And then what's the output? We can write function boxes using programming languages. So Marie is a very low-level programming language. It's actually called assembly language. And you may know a higher-level language, for example, like Python. Python, we can write our function boxes directly. So the blue text here, def add A and B, C is A and B, return C. That function does exactly the same thing as the Marie code on the left, but it's much simpler. So function machines are these simple mathematical devices, and they transform inputs into outputs. You might have seen these at school. So if we have a function machine that divides its input by 3, that's how it will work when we give it the value 75 as input. What computers essentially are programmable function machines. We give them an input, we give them a program inside the box here, and they produce an output. The inputs and outputs can be anything you like. Numbers, text, pictures, sounds, anything. But it all gets turned into binary integers inside the machine. Binary integers are ones made up of only ones and zeros. So if you've got a big picture that you've got digitized, or even this video, it's going to get turned into binary integers. Integers are whole numbers. The way that we use these programmable function boxes is that we can use them to solve a problem for us. So let's say we want to find the best route between 2 points on a map. Let's call this the Google Maps problem. The input data are the map that you've got and the 2 points. The map has to be represented in a way that the computer understands it, and indeed the 2 points as well. And it's all going to get turned into binary. The output from the program is going to be some human understandable text which gives details of the route to be taken, or it could be a picture showing how to get between the 2 points. Let's look at some actual computers. This here is the Mark I computer that was built in Manchester just after the Second World War in 1948. You may have heard that computing played a big part in the war. For example, the bombs, which was a device made at Bletchley Park. But this here was the first programmable computer that stored the program inside itself. This is a later computer, the PDP-7, which was created by the Digital Equipment Corporation, or DEC. This is in 1965 now. Typically, an organisation, a big organisation, might have only 1 or 2 of these computers, and you'll notice that all input and output is done by a typewriter device with some paper attached to it. So there's no screen, there's no mouse. This is a Cray 1 supercomputer, and now computers are getting faster and they're taking on tasks that computers hadn't taken on before. The Cray 1 supercomputer was notable because it did lots of operations all in parallel. And finally, this is the world's fastest computer, or rather it was until a couple of months ago when it got overtaken by an even faster computer. These kind of machines are massively parallel. They've got a huge number of processors, and they're used to run simulations of weather and search for genomic sequences, calculate protein folding, and all kinds of enormous computational problems. Ones which are way beyond the kind of equipment that we've got here in terms of the time taken to compute. If you take this computer and give it a task and it takes an hour, this computer would take absolutely millions of years. This computer, at least in theory, can run at a rate of 10 to the power 18 floating point calculations per second. That's 1 exaflop. So looking at these machines, you might think to yourself, well, this thing is pretty rudimentary, and this thing is amazingly powerful. I'm sure there are things that this computer can do that the Mark I absolutely can't. But there's a surprising fact about all of these machines. In mathematical terms, all computers are equivalent, in the same way that all motor cars are equivalent. All motor cars, whether they're Ferraris or beaten up old bangers like mine, they get you from point A to point B. Some of them will do it so that you get there a bit faster, but they'll all do the job. And computers are exactly the same. If a program can be run on this computer and gives you some output after a certain time, you could also run it on this computer, and you could also run it on this computer, and you could also run it on this computer, and it would produce the same output eventually. So in other words, all computers are equivalent. If you have a problem that can be solved on a computer, then it can be solved on all computers. And this fundamental idea in computer science is called the Church-Turing thesis, named after Alonzo Church and Alan Turing, who discovered it at about the same time in the 1930s. There are some problems which actually can't be solved on any computer. This may sound like a depressing fact, but we need to know what problems they are. And they can't be solved no matter how powerful the computer is. So in other words, there is a limitation to what computers can do, and we need to know that limitation. The mathematical probabilities of all computers can be exactly modelled using very simple abstract devices. One of these is called the Turing machine, invented by Alan Turing, and we can use it to reason about what computers can do and what they can't. And you'll meet Turing machines in semester 2. So, in this class, I'm going to talk about functions and computer programs. And I'm going to build up over 6 weeks to a proof that there are such things as problems that computers can't solve. You might say it like this: if P is the set of all possible computer programs, that's all the computer programs that there could be, and if F is the set of all functions which take as input a natural number and give as output a natural number, then we can say that the size of the set of functions, that's this symbol here, is actually bigger than the size of the set of programs. And therefore, that means there must be some functions which map natural numbers onto natural numbers for which no computer program can exist. Now, this might not mean a lot to you, to be honest, straight away, and we're going to build up to this proof, essentially word by word. So, for example, in this week, we're going to look at what proof is. But before that, we're going to take a closer look at what we exactly mean by computation. When I said back here that computation is what computers do, we need to unpack that a little and think about it. So there's now an article for you to read on computation, and then there's a quiz for you to do. And I'd like you to do those two things before our tutorial, which is on Thursday, the 24th of September. So they're the next 2 steps in this week's work.